In this section, we're going to explore the unit on radical expressions and rational exponents. And we begin by first exploring the properties of exponents. So your workbook that I've given out in class looks like this here. And if you can't find it, there's a digital copy on the Google Classroom. Take a look. Using the dashboard on the Google Classroom, for our monthly calendar of January, scroll down and find Radicals and Exponents workbook. Now beginning on page 3 in this workbook, properties of exponents. After this lesson and practice, I will be able to use the properties of exponents to simplify expressions. Before we learn about a new family of functions, it is important that we first pause to review exponent properties. First, a review of the vocabulary. A useful method of remembering the exponent properties is through expanded form. If the exponent of a power is a positive integer, a positive signed whole number, you can write it in an expanded form. So for example, let's say we had 5 cubed, 5 raised to the third power. This in expanded form is simply 5 multiplied by 5 multiplied by 5. 5 times 5 times 5. We know that this would equal 125, but this is what we mean by expanded form. We could also write this with a variable. Let's say it is a to the third power. Then that would be expanded out to be a times a times a. So we've got that idea down? Good. Let's check out some of the properties of exponents and summarize these rules. These will be very useful when you're dealing with, well, especially in science, when you deal with really large numbers or really small numbers. Scientific notation uses powers of 10, exponents of 10, and other exponents. So knowing the rules for exponents becomes very useful. First rule, and let us first assume a and b are real numbers, m and n are integers. Okay, so the product of the power property. Notice that the letters a and b will act as what we call the base. It is whatever is being raised to a power. So a is a base or b is a base. They're both considered the bases. The m and the n are the exponent numbers, okay, or powers. So for instance, if we have a raised to the m power times a raised to the n power, we can simply just say a raised to the whatever m plus n power would give us. So same base, you can add the exponents. Let's see an example of this. So let's say we have 5 squared, and we multiply that by 5 to the 6th power. That would result in 5 to the 2 plus 6 power, or 5 to the 8. Okay, the next rule. Power of a power. When you have an exponent, something raised to a power, and you raise that to a power. Okay, notice that the m and the n are right next to each other. In this case here, when this happens, we would multiply the powers together, so m times n. Alright, so an example of this might be if we have 3 squared raised to the 4th power. This would be the same thing as 3 raised to the 2 times 4 power, or 3 raised to the 8th power. Power of a product property. So a times b is a product. 2 could be 2 numbers, a number and a variable, 2 variables. And if they're in a set of parentheses that is raised to an exponent m here, then this is really like the distributive property for exponents. You can distribute that power to each of the elements in there, each of the factors of that product. So a can be raised to the m power and b can be raised to the m power. An example of this is, let's say we have 3x and we want to square 3x. Then we're really doing 3 squared times x squared, or 9x squared if you want to simplify that. This next rule for negative exponents is a bit of a problem when first learning this. Students mix this up with other rules of algebra. So we notice that there's a negative exponent here. This is going to be something that we're going to think about more like a fraction. So I want to think about whatever that is as putting this over 1 and making it a fraction. And then thinking about that the negative exponent is like flipping this fraction, taking the reciprocal. So I'm going to put the 1 on top of the fraction. I'm going to put the a on the bottom, raise it to the mth power, but now the power has become positive. We have rewritten this thing with a positive exponent. We don't really want to leave answers with negative exponents. That's really not a good practice. So this is how we fix that problem. We'll see a couple of examples where we use this, but for one good example here, let's say I have 5 raised to the negative 2 power. I could then think about putting this over 1 because of the negative power, thinking about it as a fraction. Flipping this fraction, 1 over 5 to the second power, and making sure that the second power is now positive. I could then continue to take the power of 5, 5 squared is 25, and write this as 1 over 25, and finish the problem. So knowing negative exponents is a good property to have in your back pocket. Another good one to note is the 0 exponent. Anything to the 0 power, with one exception, is equal to 1. So let's say I say, what is 2 to the 0 power? You'd say 1. If I say, what is 5 to the 0 power? You'd say 1. If I say, what is 100 million to the 0th power? You'd still say 1. If I went on and on and on and said, what's a Google to the 0 power? You'd say 1. And I say, okay, what is a Google plus 1 to the 0 power? You'd say, oh, wait a minute, would you say a Google plus 1 to the what? To the 0 power? Yes, anything to the 0 power is equal to 1. Now, what's the exception? Well, you can't have 0 to the 0 power. It's not actually a well-defined thing. 0 to the 0 power is really meaningless right now in our world, and it's something of an indeterminate, so we don't say 0 to the 0 power, but anything else to the 0 power is 1. X to the 0 power, yeah, that's 1. Okay, moving on. If we have a base raised to the power of m, and it's divided by that same base raised to a different power, let's say n, right, and what I'm looking at here is right here, and that would be the rule where we have the same base, so we just write the base once, a, and its power is going to be the difference of those two powers, so m minus n, subtraction. All right, it's much like what the rule is for the product. Here now we're dividing, so product and dividing. We are going to use addition for the product rule up there, and we are going to use the subtraction for the quotient rule. Now, if you have a set of parentheses with a fraction inside, let's say it's a divided by b, a over b, and we raise that thing to the mth power, then what we're going to get is we can think about this as another distributive property, sort of like what we had up here. Now this one here, we're going to distribute that power to both inside pieces. So a to the mth power over b to the mth power. An example of this is, let's say I had 2 over 5 as a fraction raised to the third power. Then I could write that as 2 to the third power over 5 to the third power separately. And then simplify it from there. You get 8 over 125 if I want. Okay, so that's a basic summary of all the exponent rules, and there's two other things we can note. We have this thing called the power property of equality, and that would just basically mean this. If we had, let's say, a raised to the power of x, And we say that's equal to a raised to the power of y. Well, since their bases are the same, a equals a, then their powers have to be the same. X must be equal to x. Then x must be equal to y, excuse me. So if a raised to the x power is equal to a raised to the y power, then x and y must be the same power. X must be equal to y. So that's the power property of equality. A common base property of equality would be something that's a little bit different than this. It would say something like this. If, let's say we have capital A raised to the second power, we'll pick a particular, no, you know what, we'll just say m, okay, raised to the mth power, and we say we also have b raised to the same power, and those two things are equal to each other, then we can say that a must be equal to b. Again, if a raised to some power is equal to b raised to the same power, then a and b must be the same number. Equality means that they are the same. Okay, in the next section, what we're going to do is we're going to check out simplifying a couple of these expressions, which is in the next few examples below, and we're going to see how we can use these properties. Simplify each expression completely. So we want to keep in mind PEMDAS, and that stands for parentheses, exponents, multiply, divide, add, and subtract. Okay, so here we have a set of parentheses and another set of parentheses. So we want to deal with the innermost set of parentheses here. Say, what is negative 3 squared first, and we're going to get 9. And once we get that, we write it out as 9 times 5 quantity raised to the third power. Now PEMDAS still says do what's inside the parentheses first. We have another set of parentheses now. So we get 9 times 5 is 45, and that's raised to the third power. Now, we've simplified the expression, and we could have also written, maybe somebody might think that, oh, they're supposed to write it as 9 to the third power times 5 to the third power. And that would be correct. But if we're following PEMDAS, we're going to do it in the way that I had just explained. So even though there are multiple ways that may come out to be the same thing, PEMDAS will never steer you wrong. Okay, so we're not really asking for what the value is at the moment. We're just saying simplify it. Learn to use the rules. All right, next one is we're going to simplify this expression by first trying to, in this example number 2, we're next going to try to do something with the exponents inside and trying to work with the parentheses first. So I notice in this particular example, 1 and 3 are not the same base, so I can't just do something with their exponents. I really can't do much with them at all. So again, I'm not trying to evaluate the exponents. I'm not using my calculator to multiply through here, so that's not the idea. I'm trying to just use the rules. So the next thing I'm going to do is I'm going to distribute that power on the outside to the powers on the inside. So remember that that's going to look something like separately distributing negative 2 power to that one and negative 2 power to that one. And so when we have a power raised to a power, we multiply their powers. Okay, again, this is the rule that says a to the m power raised to the nth power is a to the m times n power. Okay, so what we're going to get here is 1 to the 4 times negative 2, which is 1 to the negative 8 power. And then on the bottom, we're going to get 3 to the negative 4 power. Now, 1 to any power is just going to be 1, so this thing's going to simplify to 1 over 3 to the negative 4 power. So what we're going to do next is we're going to employ the rule of negative exponents, and that is that we get the reciprocal of it with a positive power. Like this, we're going to change this to 3 to the positive 4 over 1, which we can just simply write as 3 to the 4th power. That would be the simplest way to write that. Okay, and that really is two really good examples of how to use the properties of exponents. Continuing here, you can use properties of exponents to simplify exponential, expressions. A simplified expression contains only positive exponents. Only positive exponents. So that's why we have this rule for negative exponents to deal with them. And so let's go through and do a couple more examples, get more familiar with how these work. So in this one we have a product of all three things have the same base. So we can take the single base w, and then the rule was to add the exponents. So we're going to see 5 added to negative 8 added to 6. Okay, and when we add all that together, we get 3. So w to the third power, w cubed. Now, in this case, letter B, there is something we can do inside the set of parentheses if we're trying to follow PEMDAS. Okay, and what that is that negative exponent, we can take care of that. And because this is already a fraction, the r squared's not going to really do anything, then it doesn't have a negative on that one. But the c to the negative fourth power is going to get flipped, meaning that the c would go from being downstairs to upstairs, and in its place, of course, we would have a 1. So when we flip it, oops, that's got to be positive now. So that would be a positive 4. That's good. And now we have c raised to the fourth power, r squared all on top there over 1. But that's still raised to the negative 3. We haven't done anything with that yet. Distribute it here and distribute it over here. That's going to give us r to the negative 6th power and c to the negative 12th power. By distributing, we've now given those powers negative powers, and remember that when we do this, again, we're thinking about wanting to flip them. So we put them over 1 and flip. We get 1 over r and now to the positive 6, 1 over c to the positive 12, and we can just combine those together as 1 over r to the 6th, c to the 12th. And that's our final answer right there. So these are a little bit challenging. They take time. You really don't want to rush these. Now what you might notice here is that we have some numbers in here. We have a different variable m there, and we have another variable n both on the top and the bottom there. Okay, so we have 3 different types of things going on in this fraction. So when we can separate each of the parts by putting them in their own parentheses, and since m doesn't have a partner on the bottom, I'm just going to put it over 1, and I'm going to then use the rules of exponents to deal with them individually. Now 16 over 2, that's pretty easy. I'm just going to write this as 8 over 1 for the time being, since everything is still kind of a fraction here. M to the 5th over 1, there's not much to do with that. But here's the interesting part, is the n part, and we're going to use the rule that says we do for this one, n to the negative 4 minus negative 6. So that would be negative 4 plus 6. And that's going to simplify to n to the 2nd power. Okay, so we have all of this stuff going on next to it, multiplied with it. And then if we put it all together, we get 8m to the 5th, n squared, and then we can kind of drop that 1 on the bottom there, and that is our final answer for that problem. These can be tricky, but when you separate the parts and take them one at a time, it can be a lot easier. So in letter D here, what we might want to do inside the parentheses, it's a little tricky. You might be tempted to want to take care of that negative 3y inside the parentheses here first, but that wouldn't be my strongest recommendation. We might be doing something a little bit more unorthodox here, and first, distribute this 3. Okay, so that'll give us on top here x to the 12, y to the negative 9. On the bottom, nothing's going on yet, so we're just going to copy that back down. All right. Now, just like in the last problem, I have 2 variables, so let me split them up into 2 parts. So I have the x to the 12th over x to the 3rd, and then next to that is going to be y to the negative 9 over y to the 4. x to the 12 minus 3 power, and over here it's going to be y to the negative 9 minus 4 power, being very careful with those negative signs. So if we take 3 away from 12, we're left with x to the 9th. If we take negative 9 and negative 4, we get negative 13. Now we cannot leave negative exponents in our problem. We have to have only positive exponents in our solution. So this bad boy with the negative exponent, we're going to put that over 1 and think about flipping it, so that we'll get x to the 9th multiplied by 1 over y to the positive 13. And putting those together, we get x to the 9th on top here, y to the 13th on the bottom, and no negative exponents. So I hope that provided you with some really good solid examples of how to play around with the rules of exponents. And just with some practice, you'll be able to master this.